Okay, well, it's good to see everybody. A couple things. We are going to go ahead and continue from what we did yesterday. We barely got started with an introduction to sets. We'll continue that today. We'll go ahead and finish it up tomorrow. But I do want to go ahead and say that this material is not on your test Monday. The test is just going to have the chi-squared test for independence and Pearson's correlation coefficient. So, linear regression, things like that. I think I've got 4 problems on there total, 2 of each, so I don't think it's going to be too horrible. But that's coming up on Monday, and then Tuesday we're going to pass back to quizzes, go ahead and talk about any questions or difficulties you may have had. And then I'm hoping, we'll kind of see how it plays out tomorrow, but I'm hoping that we'll kind of have this done. So we may just go ahead and not move on Tuesday, because what's happening Wednesday? Okay, the PSAT, and I don't want to go ahead and give you anything the night before, so that means it's going to be quite a long period between, Friday and when we get back to it next week on Thursday. So I'm kind of toying with the idea of probably next Thursday, because I'm not going to see you guys on Wednesday either, just having probably a little bit of review over the lesson, and then give you the rest of the time to go ahead and start looking at the assignment.
Wednesday, what would be done at time?
Yes, but on Wednesday, you are going to the morning classes in the afternoon. So first period will start at 1:35, and I'll say they'll probably be about 30 minutes each. So, whoa, you okay? So you will not see your afternoon classes on Wednesday, which is really bad news, for all of you guys, because you won't see your favorite, 6-period class that day. So I know, right? I'll give you a handshake. There you go. Oh, well, thank you. Appreciate that. Okay. But any questions on what's coming up, Michelle? Yes, it starts at 1:35. Now, before that, I'm thinking the PSAT should definitely be done just after noon, depending on when the different classes start. They want us to go ahead and start by 8:20, but they'll probably go ahead and have us wait a little longer just in case we have some late students show up, because I don't believe this one's not going to be remade at some other date. I mean, if you miss it, you miss it. So that's why I think they're wanting us to wait a little bit. But we'll get you guys to lunch, and then 1:35, we'll go ahead and get you to first period.
What if we have open first period? Do we not come, or do we have to prepare?
Then I guess you're kind of free until second period. What do you normally in the morning just not show up until second period? I guess you're good then, yeah. Unless you just want to show up and be like, hi, whatever. No? Okay. So, all right. Samir, did you have a question?
Yeah, so like first period starts at 1:35.
That's what they told us in the meeting. So I'm guessing that the bell will probably ring about 1:30, and I'm guessing they're ringing the tardy bell 1:35.
Yeah, because I'll eat lunch at 1 or something.
Yes. All right. So good. Any other questions? The upcoming test, what we're going to be doing in the next couple of days, next week, any of that? Okay, well, let's see where we were yesterday. We started to talk about sets, which was any well-defined list or collection of objects. And then we started talking about solution sets. Okay, we put them within these brackets here, typically the squiggly brackets. The curvy E means is an element of or belongs to. Okay. So if there's a slash through it, of course, that means is not an element of. And I went ahead and gave you some examples. What does this little vertical segment mean? There you go, such that. Okay, but there was also one other way I could write it instead of using that. Okay, the colon worked out just fine. So these are typically read all values of x such that, and then what follows is your restriction. Okay, the actual definition you're going to use to find out what values are going to be of importance to you. And then we started talking about the classification again. We talked about in IB, there is no whole number set. It's just the naturals that we now call the cardinal numbers, starting with 0 and then all your positive counting ones. But we still have the integers, the rational numbers, and of course your real numbers. All right. And let's just see what we have here. So just a quick recap. The null or empty set is a set that has no elements. It is denoted by an actual set with nothing in it, or we could use the no solution symbol. Okay, a finite set is a set whose elements can be counted, and an infinite set is a set for which it is impossible to list the elements. Okay, like if I were to go ahead and say, I think yesterday I used the example of all reals. Okay, then there you go. You wouldn't be able to list every single reel, but it would be fun to try, right? Yes, okay, well, okay, maybe not. Okay, so the algebra of sets. Set A is said to be equal to set B if both sets are identical. That is, they contain the same elements. So we write A equals B. Now, set A is said to be equivalent to set B if, and we talked about this notation briefly yesterday, what does that refer to? The actual number of items in the set. Okay, so they're equal if both sets are the same, okay, exactly identical. We call them equivalent only if the number of items in each set is constant. So if set A has 5 items and set B also has 5 items, doesn't matter what they are, the elements themselves may be different. We say they're equivalent, but we wouldn't say they're equal. Okay? And then you're going to see these symbols as we move through, starting in the next lesson, logic and truth tables. Those are going to start to come up a lot. All right. So we have an example here. Set A is made up of 10, 20, 30, 40, 50, and set B is equal to A, B, C, D, E. Now, set A is equivalent to set B, because if I were to go ahead and write it out using notation, N of A, you'd say what? 5. Okay, so N of B is equal to 5 as well. Okay. So they're equivalent if they have the same number of elements. They're equal if they are the exact same sets. Okay. And now let's go ahead and talk about what's called a subset and a proper subset. And there's really only a small difference between what we call a subset and a proper subset. But put simply, a subset is a group contained within a larger group. Okay, let me go ahead and make an analogy using the campus. Like, we're the only people who belong to math studies 6th period. Okay, we form our own group, but we're all part of something larger, you know, the LHS campus. We're all Westerners. So our group within a group, we could say we are a subset of Lubbock High. Does that kind of make sense? Okay. So we have these definitions here. And you also have equality. So the sideways U tells me we're dealing with a subset, but the bar tells me if the two sets are going to be equal. Okay, now remember, equal, we said a second ago, they are the exact same sets. Okay, so we can have equality when dealing with subsets, but that's the difference between a subset and what's called a proper subset. Okay, you can't equal the original group. And I've got some examples here to kind of help you out. They've got A is equal to green, yellow, and blue, right? So for the subsets of A, you have, what do we call this when there's nothing in it? That's the empty set, the null set. So we have one set green, yellow, blue, green, yellow, green, blue, yellow, blue, green, yellow, blue. If it's a subset, okay, the group itself can be a subset, okay, because the group only has those 3 elements, right? Okay, but that's the difference between a subset and a proper subset. Take a look at all the proper subsets. Again, we have the empty set, right? Green, yellow, blue, green, yellow, green, blue, yellow, blue. But am I missing something? There you go, the set itself. That's what the difference is. When you're talking about a proper subset, the set itself cannot be a proper subset. We say the set itself is a subset. That's the only difference between the two. And that's why you'll notice on a subset, you can have equality because the group itself can be a subset. But when you're talking about a proper subset, you don't have equality because that can't be the case. Yes, ma'am.
So how can they make these subset, or how can they set part?
Well, because by definition, it still is a set. It just has no elements.
So the empty set would be a subset of all sets.
Yes, that's exactly right. Okay. And, you know, for example, well, I don't know if we've got to the point yet. Do you guys remember intersection and union?
Yeah.
Okay. We're going to go ahead and start looking at those in just a minute. But because she asked the question, let me just throw one out. Let's say we have set A is going to equal to 1, 2, 3, 4. Okay. And let's say set B is equal to the null or the empty set. Okay. Now, what's the difference between intersection and union? Hey.
Union's a combination of both sets.
There you go. Union is I'm going to combine every element from both sets into one brand new one.
The values that are in both sets.
And the intersection is what they share, what they have in common. That's exactly right. So let's say I have these two sets defined, and I'm asking you, okay, I want the union of A and B. Well, even though B is the empty set, there's nothing there. The union, the combination of the two, would still be that original set. 1, 2, 3, 4. Now, what would be the intersection of the two?
Nothing.
Nothing. There you go. There's no solution. Okay. There's nothing that's in one that's also in the other. Yes.
What is the symbol for intersection?
Oh, intersection? A normal U is what we use for union, so an upside down U is what we use for intersection. Now remember, the sideways U, that means what? Starts with an S. Subset, yes. That's the group within a group. What was that? Or maybe I'm old, I'm just hearing something. Hey.
So, there's an intersection. It would be like a
Probably undefined is what we would typically say. I know, yeah, it starts to get a little crazy, yeah. Mm-hmm. Okay. So is everybody okay with the idea of a subset? A group within a group? Is everybody okay with what we know as a proper subset? Okay. It still has all the groups within a group, except the proper subset cannot contain what? The group itself, yes. Okay. A good way to think about it is that when you're dealing with proper subsets, okay, the original group always has to have at least one element that is not in the proper subset. Okay. There we go. Okay, good, good, good. And now we have some symbols here that we've been looking at. Remember, what does the curvy E mean? Belongs to, is a member of, okay. And now the sideways U, we know that is a subset. Now, is this the subset or the proper subset? The subset has the bar below it because a group can be its own subset. Okay, so it can have equality. So I went ahead and broke this up for you. We have correct usage. So for example, let's have a set made up of elements 1, 2, and 4. So I can say 2 belongs to this set right here. Okay, but I wouldn't go ahead and say that 2 is a subset. Okay, because see here, 2 is an element. 2 is not its own set. That's not how we defined it. Okay, 2 is an element, not a set. Now, if 2 was a set, then you could go ahead and make that argument. Okay, and la 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 la. Yes, 2 is a subset. I'm sorry, I got completely. I was looking at incorrect when I started talking about that. That is completely my fault. Okay, so yes, 2. If you go ahead and put it in the brackets, is going to be a subset. Yes, that is correct. All right, but if you were to reverse that, that's my fault. See, we're not going to say a set belongs to because it's not an element. See, a set is a subset. A set isn't an element of the original set. Okay, now I'm saying it correctly. There we go. So like this right here, 2 is representing an element, not a set. So an element can't be a subset of a set. Now a set can be a subset of another set, but an element is either going to belong to the set but not be a subset. I know I'm saying a lot of the same words over and over again. Okay. But this is making sense?
It's making dollars.
It's making dollars? Hey. Well, hopefully by the end I can change your mind.
No.
Change. Okay. So let me give you another example. Let's say that set A is going to equal, how about 5, 6, 7, 8? Okay. Now, we want to go ahead and write some correct ways for dealing with these. My elements, I've got 4 of them, right? 5, 6, 7, and 8. So let's go ahead and use this curvy E, the belongs to symbol, correctly. I can go ahead and say that 6 belongs to 8. Because each of those items itself is just an element, right? Okay, so that element belongs to that set. Okay, but see, here's the thing. What this is trying to tell you right next to it, if I did this, 6, okay, I can't say that that belongs to A. Because, say, when we're talking about the elements, they belong to a set. But a set itself doesn't belong to a set. It's a group within a group. It's a subset. So that's where we're making sure to use the correct notation. Okay, I'm sorry. Can I repeat that? Okay. So remember, the difference here is basically trying to decide, are you talking about an element, an individual item, or are you referring to a set itself? If you're talking about an element can belong to a set, but a set can't belong to a set. A set is a subset. It's a group within a group. So that's why we have the notation here. See, 2, an element can belong to a set, but a set doesn't belong to a set. A set is a subset of another set. It's just the way in which we say it. And I keep saying the word set a lot, so I don't know. Hey, Eli.
What's the difference between a subset and a proper subset?
A subset and a proper subset. A subset can have the group itself, but a proper subset cannot.
Proper subset.
Yes.
Have like
So like on this guy right here, okay, let's go ahead and say, would 5 be a subset? Yeah, would also be a proper subset because the original set has at least one item more than what's in this one. Okay. So I could say that the group itself, 5, 6, 7, 8, is a subset, but I can't say he's a proper subset. A proper subset can't be the original group, but anything smaller, yes, that's a proper as well.
It has to be with the side with the line.
Yes. So the side U with the line, that's a subset. I can include the original group. Without the line, that's a proper subset. Okay. Hey, so.
So earlier you were talking about like how you use like how you determine if you talk about elements or subsets.
Mhm.
Like would you just determine that based on the symbol that you see?
Yes. Yes, yes, yes. So like if I were to, let me give you a completely different set here. Let's say we have A, B, C, D. Okay. And I'm going to give you 2 statements. Let's say B, but let's call this set, I don't know, F, just so we don't have to use the same letter. So let's say B belongs to F, or set B belongs to F. And then right below that, let me go ahead and do this. B is a subset of F, or B is a subset of F. Okay? So let's run through these. They're either true or they're false. Okay? Now you'll notice here, if I just wrote B, am I referring to an element or a set? I'm referring to an element. It's only a set if you put it in what? The brackets. So can this belong to F? See, that's true. Okay? An element can belong to a set. Okay? Now, this right here, because I put it in brackets, what? Okay, so can a set belong to another? No. So this one is false. See, it all depends on the notation. So now if I go to the next one, can I say that the element B is a subset of F? No. Okay. Now a set can be a subset of another group, but an item itself can't be a subset.
So in order to declare B a subset of F, we have to make it its own set.
You'd have to put it in the brackets. Yes. That's exactly right. Is it starting to make a little more sense now?
Yeah.
So your item has to be either defined as just an element or as its own set. So what about this last one? Would that be true or false? True, because I have it listed as a set, that one would be true. Michelle,
What are we writing in those blank spaces?
what are we writing in those blank spaces? Oh, we're going to get there. We're going to get there. Okay. All right. Do I need to give you another example, or do we feel like we're starting to get the idea? Give another example? Okay. Give me some more items. Q. Q, M, P, O. Okay. So let's say we have this set right here, and let's say this is, let's call it set Z. Okay. So give me a correct sentence, or a correct statement, I should say, using an element. Okay. Say it again, Gabby. Okay, so Q belongs to Z. Now, when you say belongs to, are you talking about the sideways U with the line, or are you talking about the curvy E? The curvy E. Okay. An element can belong to a set. A set doesn't belong to another set. A set is a subset of another set. Yes, sir.
Set MPO is a subset.
Is that true? Yes. Okay. Okay. Now, it would even be true if I went ahead and took that off. Remember, if I remove that bar, that now becomes a proper subset. The only restriction for a proper subset is that the smaller group not be the entire group itself. But with that, that's a subset. I can go up to the entire group. Okay. Can I make this statement here? Can I go ahead and say that, let's see here, P belongs to Z. Why not? I see P right there. Because I made P a set by putting it in brackets. Okay. So set P doesn't belong to another set. Set P would be a subset of the other set. That's the notation. Michelle, is this kind of helping out? Okay. Are we sure? Right. Any questions? Hey.
Just to be completely sure.
Yes.
It can be a proper subset as long as it doesn't have every element.
Yes. So like the only way a statement like this, if it didn't have the bar, would be false, is if I were to say in this case, Q, M, P, O. Okay. Again, why would that be false? There you go. With the proper subset, you cannot say the group is the set itself. Now, if I had the bar below it, that's a true statement. The subset can include the entire group itself. But without the bar, the proper subset can't have that. Okay. Mm-hmm. Are we good? Michelle? Okay. Okay. Ready, set? I don't think there's been a day where I've said set so many times. It's just subset, set. All right. So good. Let me make sure that I didn't forget anything. Okay, I just scrolled down so I could write that. So everybody's okay now with what the table is telling you? You just want to make sure that your item is defined either as an element or a set, and then use the correct notation. The curvy E only goes with an element. Okay. The sideways U only goes with sets. Okay. So let's see. Now here's what we were just talking about a second ago. Intersection and union. The intersection of two sets is the set of elements they have in, and Eli actually said it just a second ago, common, and is denoted by this symbol. It's an upside down capital U. Okay, so let's see here. Here's an example. A is made up of all even numbers, so 2, 4, 6, 8, and it's going to keep going. B is all the prime numbers, and what does prime mean again? There you go. Any value that's only divisible by 1 in itself. Well, what I'm told here is that the intersection of the two is 2. Okay, 2 is actually pretty unique. He is the only even prime number in existence. So if I were to go ahead and list these out, okay, maybe to help somebody see it, 2, 4, 6, 8, and it doesn't say a limit, so I have to believe that this is an infinite set. Okay, the same thing with this. What can you say about prime numbers?
1, 3, 5, 7,
Oh, you forgot one. 1, 2, 3, 5, 7, ... Okay. Well, the intersection, you're only looking for what each has, what they have in common. Okay, so it's just 2. Yes. Mm-hmm. That's exactly right.
Would after 7 be 11?
Yes. Yes. Mm-hmm. Okay. All right, so is everybody okay on the idea of intersection? Okay. Well, let's take union. The union of two sets is the combination of all elements in what? In both sets. There you go. Both. Each element only being listed once. So if you do have items that repeat, you don't want to go ahead and list them again. Once is sufficient. I always like to think of union as a marriage of the two sets. I'm going to take everything from one set and combine it with everything from a different set to make one larger set. Okay? It's a marriage of the two, but union's okay. There you go. And here's our example. The letters in the words mathematics, and then A, B, C, D, E. So you'll notice I took every letter that we had in mathematics, and even up here, some of them do what? They repeat like the T's, right? But I'm only going to list it once. Okay. Now, are there any letters here in B that are not in mathematics? Okay, D, for example, B, but you'll notice they're part of the union. I'm going to take everything from here and just combine it with everything from the second one to make a brand new set. That's the union. Hey.
But writing like sets, do we have to write the numbers in numerical order?
It depends on the teacher. I kind of prefer that if we're dealing with variables, we put them in alphabetical order, and if we're dealing with values, we go ahead and put them in numerical order. But it depends on really on the teacher. Did you ever have any that didn't care about that?
Yeah, I quite a
Okay.
but it's just
For me, it's not really just being a stickler about it. It's just like if you're going to grade something, it just makes it so much easier if they're in order. Yeah. Yeah, that's fine. Okay, good. All right, well, let's see what else we got. Okay, the number of elements in a union of two sets. This is an important concept in set theory, and we're going to be seeing this when we get to probability. Okay, so what does it mean if I have n outside of parentheses for a set?
Number of.
Okay, so this says the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the what? In the intersection. Okay, we have to subtract off the number in the intersection because we don't want those values counting twice. Remember, the intersection is what's in both sets at the same time. Now, here's a super important idea. What we call complements. Complements of sets and the universal set. Okay, so the universal set, you're going to start to see this a lot, is always denoted by U. Typically, especially when we start getting to Venn diagrams, the entire universe you're talking about is just going to be represented by a rectangle. And within that rectangle, you're going to have the different groups that you're talking about, the different sets. Okay, so if it doesn't belong to the universe, we're not going to go ahead and count it. Now, the complement of set A is all of the elements that are in the universal set, but are not also in set A. Okay, so here's our example. U is going to be the letters in the word universal. Okay, so set A is A, E, and I, right? Let me write this out so that I can actually help you see this a little better. So let's say this is set U, right? The complement refers to all of the elements that are still in the universe, but not in the set you're currently talking to. Okay? So think about this. A has A, E, I, right? So A, E, and I want to remove those from the universe. Okay, so A, E, and I. Whatever's left is the complement. That's why we have the LNR SUV. Okay, it's everything in the universe, but not in the set itself. Okay, so let me go ahead and give you another example of that. Let's say that the universe is going to consist of the numbers 1 through 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And let's say set A is going to be, I'm just going to randomly choose some numbers, 2, 3, 5, 8, and 9. Okay. Okay, so the universe is only containing these 10 elements. There's nothing else. I'm going to say set A is going to be 2, 3, 5, 8, 9. Okay, now by definition, the complement is every element in the universe, but not in its respective set. And we always denote it with a little tick mark where a power would be. Typically from geometry, you might have said prime or something like that. Okay, so that's our notation for complement. So what do we see that's in the universe, but not in A?
1, 4, 6.
There you go. That's it. That's what the complement is. Okay. Is that kind of helping out a little bit? Okay. And the same applies if you're looking at variables or anything else. Okay. Now, with this idea, okay, if I take the union of A and its complement, well, that's going to go ahead and give me the universe, right? And that makes sense. Look at the example that I just gave you. Okay. The universe is everything 1 through 10, right? So if I took set A and took the union with its complement, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The union will get me right back to the full universe. Okay. The next statement is going to talk about the intersection. But it says the intersection of a set and its complement is what? Is nothing. And that makes sense because if I look down here, what do the two sets share? They have nothing in common. And they shouldn't by our definition. Okay. Questions on that? How are we doing? Good? Okay. Yes?
Are we gonna write it on like a paper like union and then a big union?
Oh, yes, when we start with the Venn diagrams. Actually, we're just about there. Okay. All right. So let's take a look at this. And there's one other idea here. So the number of elements in set A plus the number of elements in A's complement is equal to the number in the universe. And when you really start to look at these and you get some more practice with them, you'll really start to see that these make sense. Okay, they're going to be true. All right, Venn diagrams. These are where the fun starts. So disjoint, this is another vocabulary word that we can have. The sets are disjoint if they have no elements in common. Okay, so here's what I was referring to a second ago. You're going to have a rectangle representing your universe, and then you're going to have different numbers of circles, or what we call sets, circles representing those sets inside the rectangle. So if there's no overlap, no connection between them at all, what we call those disjoint. Okay. If they intersect, if they have only a few elements in common, well, then they'll slightly overlap. Okay. Now, a subset, if all of the elements of one set belong to a larger set, you can actually show it by using this, having a circle within a circle. Okay. Kind of like if we were to draw a Venn diagram of Lubbock High, our 6th period class would be contained completely within the school. All right. Yep.
It looks like an avocado.
An avocado? I guess it does. Okay. I probably would have said like, that's a horrible eyebrow. Okay. Everybody knew where I was going with that, right? No? Really?
No idea.
Okay, let me. Is that better?
No.
Really? Oh,
It looks like eyelashes.
yeah. This. Yeah. So this be the eye. This is the. Okay. I'll make it a cat.
Yeah.
Well, it's like a cat's eye.
The cat's eyes aren't ellipses like that. It feels like circular.
An evil cat would. Halloween's coming up. You know what? I'm going to go home and I'm just going to stare into my cat's eye just to see. So I'm going to go home tonight. I'm just going to grab my. Oh, Eli was right. Okay.
Bring your cat here so we can all.
I don't think you want me to bring my cat here. My cat's weird.
Wait, your cat and Mr. Tao's cat should become best friends.
Who?
Mr. Tao, he has a cat named Dorian Gray. And
Really?
Yes, and your cat and his cat could become best friends.
Nice.
And then they could go on cat adventures together.
So if I were to bring him up here, he could help me out.
Yeah, he could.
No, that is an amazing name though. I have 2 cats. One is named Murphy,
Oh, God.
and the other one's name is Murdoch.
Yeah.
But not probably what you're thinking. When I say Murdoch, it's only M-U-R-D-O-C. A lot of people immediately think it's Murdoch, Matt Murdock
Yeah,
from
that's what I was
Marvel, Daredevil, but it's actually a MacGyver reference. Murdoch was his sworn enemy throughout the entire series. The one person he could never defeat, and MacGyver was the one person that Murdoch could never defeat. Did anybody ever watch the old MacGyver? Not the new ones. I'm talking about the old classic MacGyver. Yeah.
Wait, what's
Are you just making me feel better, or are you really going to?
Oh, I have.
Okay.
Wait, you didn't guess what's the guy? I told you think I was.
Really? No. We're talking about the guy who could, make a bomb with a piece of paper, chewing gum, and a paperclip.
What? This sounds like
That was the whole purpose of the show, was that he would repurpose items to help him in different situations. He was like a spy of sorts. He worked for a foundation called the Phoenix Foundation. It was like a think tank. It had Richard and Dean Anderson.
Dude, I need to watch this show.
It was a great show. It was on for what, 8 seasons in the late 80s and early 90s. It's what the new MacGyver is based off of. And I'm not completely sold on the new MacGyver yet. I don't know. Oh, that my wife named him. Is anybody in here a Boondock Saints fan?
Yes.
Okay. She named the cat after one of the brothers in the movie.
It's a movie. It's awesome.
It's a great movie. It was originally supposed to be released in the theaters, but unfortunately, right before its release, Columbine happened, and it's a very gun-violent movie.
Oh.
So
Oh yeah.
they went straight to DVD. In fact, they came out with a sequel, and I liked the sequel. I thought they still did a pretty good job. They're supposed to be coming out with a part 3. Yeah, and my wife, she's big fans of Norman Reedus. So yeah, it's pretty cool. I'll tell you what. We kind of got off topic a little bit, but that's okay. I'll tell you what. It's already 2 o'clock. Why don't we just go ahead and stop there? Because we actually don't have a whole lot left to do, and we still have tomorrow, so I'm okay with that.
Whoever watched